Hi guys, hope you're having a really good spring break. Like I wrote to you in the email yesterday, I've kind of changed some things around a little bit. I want to focus on chapter 27 and 28 in these videos that I'm going to post today on the blog. In chapter 27, some of this stuff will look a little familiar to you because over maybe like a month or two ago, I had you watch those videos, and they were about like the photoelectric effect and the Compton effect and things like that. That's what these chapters are about. So I'm all by myself here at school because someone was supposed to come and video for me last week, Doug, but did not. So I'm going to be kind of moving back and forth. It may be a little bit difficult for you guys. You're going to need to make sure that you keep your slides out with you so you can follow along, because I'm not going to be able to like project the slides and then do everything and teach kind of at the same time. So you're just going to have to try to follow along with me the best that you can. So the best thing I can tell you is to get your slides out and kind of follow along as I'm talking about a lot of these. In chapter 27, it's a lot about how classical physics doesn't work, and maybe some faults with classical physics, and then where modern physics kind of began, or where it started. So there's not really a lot of math in this. There is a little bit of math, so I'll probably stop the video, write it all up on the board, and then we can walk ourselves through it. So you're just going to have to kind of bear with me because I have to do all of this stuff on my own since Doug decided not to come in and videotape for you all. Okay, so let's start on chapter 27, and this is all about quantum physics. You'll see that starting on slide 2, this is where we're starting off with Planck's hypothesis. In the 1800s, there was a problem faced by scientists. It was the end of the 1800s. There was a huge problem. This problem was we don't know how to explain the spectra of electromagnetic radiation that's emitted by objects. Now, you know electromagnetic radiation is. We know that electromagnetic waves, or any wave in general, is just a transfer of energy. So we know that electromagnetic radiation is just a type of energy that doesn't need a medium to travel through. It can travel through a vacuum. We know that electromagnetic radiation is dependent on electric fields as well as magnetic fields. And at this point, at the end of the 1800s, when I say that we have a hard time to explain spectra, actually, let me try to pull something up for you right now on the computer to show you what I mean by that. What I mean by spectra, which I should have done this before, but I didn't. I'm sorry. Okay, here we go. We're going to talk about these two, but this is what I mean by spectra. I hope you can see this. Okay. So you'll see here that there's some different types of spectra. The top one is called a continuous spectrum. And all that means is you're seeing... Oh, sorry guys. Okay, all that means is that you're seeing all of the colors in the visible spectrum. So we know like the spectrum just has different categories. Just like in an electromagnetic spectrum, we have, you know, we're starting off with radio waves, then we go to microwaves, and then we go to infrared, and then we go to visible. That's a spectrum, so there's categories. And that continuous spectrum that you just saw, there are all the colors, so there's Roy G. Biv. So we know that that's a spectrum. Now, underneath those were something called an emission spectrum and an absorption spectrum. And we're going to talk about those in just a little bit. So I actually think that that's in chapter 28. Let me make sure. But we will be talking about those. Or maybe it is in this chapter. Nope, we will be talking about it in this chapter. So this is when we get to like section 4 in this chapter. So we'll talk more about it then, but I just wanted you to understand what I mean by a spectrum. So scientists would do these experiments with different amounts of energy, and every time they would get a different spectrum, and they didn't know why they would get like really dark bands and then like one colored band. Why they'd see more dark band and then they'd see another color band. So let me show you what I mean by that. Bear with me, guys. Okay, so you can see here that this is a dark band, and then there's a colored band here. There's another dark place here, and then there's like a purple colored band there. That's an emission spectrum. An absorption spectrum is where we see lots of color, but then randomly we see these like dark black, very thin bands or thin lines. So you can really see that dark band in between the orange and the red here, and that's an absorption spectrum. What that means is, where you see, let's look at just the absorption spectrum, where you see lots of color, and then there's just a few of those little tiny dark bands. At those really tiny dark bands, that's where all of the light, all of that energy is being absorbed, versus you have a lot of light in different colors that's being reflected, and that's why you see that continuous spectrum there. That's why you see all of those colors. In the emission spectrum, where you see more dark bands, but then you see like a few very thin strips of the colored bands, that's kind of the opposite. So all of the light in this case is being absorbed, and then there's just a there's just a little bit of light that's being emitted, and it'll be in different colors. So scientists back then did not know how to explain these things, because it seemed to them that any different type of element or any different compound that they tried to see if it would absorb or if it would emit, it always had a different spectrum. So they were really confused by this, and they didn't really know what was going on. So still on slide number 2, that's kind of this problem that they're facing. And I wrote here thermal radiation. And all that means is thermal radiation is just the amount of energy that can be emitted by an object. So a light bulb would definitely have thermal radiation because it's able to emit some type of electromagnetic radiation out to you. You feel it as heat, you see it as light. That's definitely a type of thermal radiation. So that's what we mean by that. At everyday temperatures, a lot of radiation is in the IR region, so in the infrared region. So for us, most light is what we feel as heat. So we actually feel it instead of seeing it. It's at 1,000 Kelvin, which is super hot, super hot. At 1,000 Kelvin, it emits some type of reddish color. So typically when we get to about 1,000 Kelvin is when we can see some type of energy that's being released in the visible spectrum. So at 1,000 Kelvin, we typically see red. So a really good example of this would be like your stove. And especially for like an electric stove burner, you can see that red color. That's typically at about 1,000 Kelvin. So that's why we can see it, because it's emitting energy in the visible spectrum. And then in this case, it's red. So it's emitting a certain type of wavelength. At 2,000 Kelvin, that would be still in the visible spectrum, and in that case it would be emitting like a yellowish, whitish type of color, and that would be like the filament that's in your light bulb. So temperature has a really big effect on the intensity of light, or the type of light that we see. So temperature has a very big effect on intensity or the type of light in which we see, okay? Keep that in the back of your mind. Now, typically, whenever we look at a light bulb, or if we look at the stove, we observe some type of dominant color. Now, nothing is 100% efficient. So that stove, we see that on the electric stove that the ring around, like where you keep your pot at or your pan at, is red. But there are also other colors that are being emitted. It's just that the dominant color that our eye is seeing is red. Okay, so that's what I mean here on this next part on slide 2, where it says, although we observe a dominant color, there is actually a continuous spectrum. So there are other colors that are being emitted. It's just that most of the color that's being emitted on like the stove, for example, would be red. When we have a light bulb at 2000 Kelvin, most of the light that's being emitted is in the yellow or the whitish color. It's not so much like greens and blues, but there are a few of those colors that are being emitted. So in a light bulb, there's still some of those colors being emitted. It's just we mostly see like a yellowish color or a whitish color, okay? On this same slide, on slide number 2, I wrote at the bottom, this spectrum shows that the intensity is dependent on wavelength. So the reason, I didn't mean to write that on that one, I should have written that on slide 3. So if you'll look now at slide 3, there's a graph here, and it says A. So you want to look at the graph that's A, and there's 3 little bumps on this graph, and you'll see that on the y-axis, it's intensity, and on the x-axis, it's wavelength. So wavelength is X, your intensity is Y. On this is a graph that's trying to show you that intensity is dependent on a wavelength. It's also trying to show you that intensity is also dependent on temperature. So if you look at this graph, at the bottom of this graph, again, it's the x-axis, and that's a wavelength. You'll see that it labels for you like where UV is, and then it labels for you where visible is, and then it starts to tell you at the bottom where IR is. So you'll see here that IR is starting almost around like 1,000 nanometers, because the wavelength says here that it's measured in nanometers. Now we know that visible light has a specific amount of wavelength, and we know that that wavelength is from, at this point in time, I hope that you're screaming those numbers out at this video because you should know this, but it's from 400 nanometers to 700 nanometers, and we know 700 nanometers is which color? That'd be red, and the 400 nanometers would be violet. So 400 nanometers violet, 700 nanometers red. On this graph, they're trying to show you that at the 400 nanometer, that would be the very tall peak here. Be the very tallest peak where it kind of says that little lambda max, and then it says T3 really close to it. At that peak, that would be mostly where you would see like a violet color. At the next, let's look at the one that says like T1. I think that's a good one, at T1. That's the very smallest peak. That's a little bit past the red color. So that's even like out of that visible spectrum. So we're not even going to be able to see a color there. But there's not very much intensity because we can't see it. At T2, that's probably where your red color would be. So there's a little bit of intensity. I want to think about what I mean here when we say intensity. And intensity just means like the amount of energy that's being emitted or the amount of energy that we're seeing. We talked about before that wavelength and frequency have an inverse relationship. So when we think about energy, we know that frequency has the same relationship as energy. So as frequency gets bigger, the energy also gets bigger. So as frequency increases, energy also increases. But wavelength does the opposite. As energy and frequency increase, the wavelength actually gets smaller. So violet light is closer to UV rays, and we know that UV rays is where the wavelength is getting smaller, and then after UV is X-ray, and we know those are even smaller, and after X-ray is gamma, and we know those are the smallest. So those, as we move from red to violet, we know that the wavelength is getting smaller, so we know the energy of those light waves have to be getting greater. So red light doesn't have as much energy as violet light does. So violet light will have the most energy, which means it's going to have the most intensity